iTech is an AI tool that can be used in product support. Its main use is for diagnostics to reduce MTTR, but it is also excellent at interpreting error codes and identifying redundant bit. iTech can generate fault trees and testability analysis that can be used to improve design for supportability. It can also assist with fault mode and effects criticality analysis as well as root cause analysis. The entire product lifecycle should be part of your supportability analysis as your design influences things such as testability, support tool requirements, MTTR and so on. iTech can be used to perform FMECA analysis once the model is built, to analyze the effects of certain failures, determine criticality of components, identify the necessary tests and replacement components for optimal MTTR in the field. Once built, the model contains all the data necessary for a field service engineer to troubleshoot and repair a system. With careful modeling and the built-in feedback and learning mechanisms, it can also be of help with root cause analysis. When it comes to built-in test, there are often hundreds of error codes. These don't necessarily identify the root cause of failures, and therefore still require interpretation or diagnosis to get to the root cause. The iTech model takes all these test results or bit, and automatically translates it into root cause, or an ambiguity group. One example is the Transrapid maglev train in China, where iTech monitors over 120,000 components in real time. Typical systems nowadays are hybrid devices containing mechanical and electrical hardware, as well as software components, often with bit-in monitoring. iTech can be embedded or used in a manual mode to assist in fault diagnosis. Let's look at a typical example of a key crane. One would start with a functional breakdown analysis. In this case, we are only going to use the hoist brake as an example. When the operator activates the joystick to raise or lower the container, the signal is sent to a PLC which contains the control software. It also gets some safety interlocks to prevent accidents. The software then checks whether the correct combination of signals is present before sending the brake release signal to the PLC output, which activates the two contactors to send power to the two brakes to release the hoist drum so that it can rotate. Here you can see the various input and output circuits in the model. The software is also modeled, showing the relationship between the inputs and outputs of the PLC. Modeling is done by drag and drop from the parts database into a dependency model, and component properties such as test and repair procedures, and the time to perform them, can be added, as well as other data that may be used during a fault finding and repair session. Once the model is completed, fault tree analysis can be done for various types of failures. This will then give us an estimate of the MTTR, ambiguity groups, etc. for different scenarios. During this runtime fault-finding session, you can see that if we select the symptom where only hoist brake 2 isn't activating, the system deduces that as brake 1 is working, only the circuit for brake 2 can be suspect. This leaves us with an ambiguity group of 3 components to test. On the other hand, if the symptom is just hoist brake problem, that leaves us with the entire hoist brake circuit to test. By selecting a component, say contactor 41, and failing that, we are simulating a fault and performing a fault mode and effects analysis. We can see that brake 1 will not be affected, and thus we will still have some braking effect. Using this method we can simulate the effect of different failures on the system functions.